A lot of waste heat is generated at power plants, and power plants need a way of moving this waste heat away from their location. People have engineered two different ways of doing that. The first is to construct evaporative cooling towers at those locations where water is evaporated, and then the second type is just to dump all that waste heat into the rivers. The first option reduces river flows, whereas the second option increases the heat in the river.
What we don't know regarding electricity production are the trade-offs of relying on river systems for conveying waste heat away. We had three goals. One is to understand how much power generation in the region depends on rivers, how those rivers are impacted by power plants, and then how the rivers themselves help support energy production and minimize impacts downstream.
So we have a pretty well-established hydrological model, and we've linked this with a thermoelectric power plant model. And so that the two models run dynamically and they interact with one another, so that water temperatures and river flow impact power production, and power production impacts river flow and water temperatures.
The model was regional, to incorporate a bunch of river systems across the climate gradient. We focused on the Northeast because that's a heavily populated area. There's a large demand for electricity, and as a result, there are also a lot of power plants in the region.
It's spatially distributed so that we could get upstream and downstream linkages, so that impacts upstream also affect power production downstream.
What we found was that of the total heat produced to generate electricity in the region, roughly a third is actually converted to electricity, and the rest is waste heat. Of the waste heat, roughly half is returned back to the atmosphere through evaporation of water, through vertical cooling towers, and the other half is transferred to rivers, which then convey that heat away. Waste heat that is returned to the atmosphere through vertical cooling towers evaporates water, and so that uses water consumptively from rivers. What we found was that there's a relatively small proportion of the total flow actually is lost that way. Of the heat that's transferred to rivers, we found that the vast majority of it actually is conveyed all the way to the ocean, whereas about 10%, a little over 10%, is conveyed back to the atmosphere.
So the impacts to river flow are pretty minimal, which suggests that these power plants are well managed here in the Northeast. The impacts to water temperature are more severe. There's about 7,500 kilometers of river length downstream of these power plants. And this map shows the increases above average summer water temperatures. This has pretty significant implications for aquatic fish habitat, and we found a decrease in suitable habitat for native fish in the region. These increased water temperatures also provide a foothold for invasive aquatic species, and so this further degrades the aquatic ecosystem in the region.
So the implications of our work is that we can now begin to integrate economy, energy production, hydrology, and climate to understand the impacts at a regional scale.
So we rely on these rivers to cool power plants at these locations, but there's a trade-off because this impacts aquatic fish habitat and aquatic ecosystems. So our model is a wonderful tool to understand these trade-offs, especially in a world with an increasing energy demand and changing climate.